Hello friends, welcome back to my YouTube channel. I am Maths. In this video, we are going to discuss the application of Bernoulli's equation. So, in the previous lecture, we have discussed that Bernoulli's equation is basically the equation of the fluid motion, and now we'll discuss the conservation of the energy in the Bernoulli's equation using a practical example. So in this practical example, we have a tube in which area of a cross section, this part is A1 and the area for this part is A2. Here the fluid goes with the force F, and obviously with the, and here is the force is on, or we can say that atmospheric force in this way, that F. Now the velocity of Q at this surface is Q1 and velocity at this is Q2. Okay, then this is at delta x1 and this is delta x2. Okay, so the height from the free surface for this is particularly, we can say that it is our reference line or the head line. Basically this is our reference line. Then by this reference reference line will take the height. So basically the height for this cross section is h2 and for this cross section is h1. Okay, so this is the height. So we'll represent the height is basically h1 and h2 from this reference line. Okay, now here the pressure is P1 and here the pressure is P2, density is rho1, density is rho2, where rho1 and rho2 are equal because the density of water or like whatever fluid we will pass from this tube will be constant. Now, first of all, what is like to identify or to prove the conservation of energy, will start with the work. So work is nothing but here the force and the distance traveled by this. So basically work done for this is nothing but it is W, that is basically the F1 delta x1 minus F2 delta x2. Now the force is represented in the way of the pressure, or basically we know that pressure is nothing but the force per unit area. So we can write in this way, the pressure at first part it is P1 and area is V1 into delta x1 minus here it is P2 del or A2, area is A2 into del x2. Now in this case it is P1 and it is the volume, I say V1, where V1 is the volume at V1 and V2 are the volume at parts or at the end. Okay, minus it will be P2 V2. Now because of that here volume will be same and pressure are not same, but volume will be same. Then V1 minus V2 and V1 is equals to V2, that volume will be same, it is nothing but some V. I will consider it as V. In general, the work done is basically, in general, the work done is basically the sum of kinetic energy and like basically these are two energies. Okay, yeah, the kinetic energy is 1 by 2 mv square at point q2 minus 1 by 2 m q1 square, and this is basically the mgh, then mgh2 minus mgh1, it is with the difference. So it is W and we have calculated the W is P1 minus P2 into V is equals to 1 by 2 m Q2 square minus 1 by 2 m Q1 square plus mgh1 minus mgh or h2 minus h1. Now we can find the Bernoulli's equation or the relation in this way. We have we will take 1 by 2 m q1 square plus mgh1 plus p1 v is equals to 1 by 2 mg q2 square plus mgh2 plus P2 V. Okay. Now we have m by v. We will divide v, then it will be 1 by 2 m by v q1 square plus m by v gh1 plus p1 is equals to 1 by 2 m upon v q2 square plus m upon v gh2 plus p2. Yeah, divide v. So it is nothing but density. So 1 by 2 rho q1 square plus rho gh1 plus p1 is equals to 1 by 2 rho. Basically this is the like density will same, rho 1 and rho 2 will same. We will represent this rho 1 and rho 2 as rho. Okay, so it will be rho q2 square plus rho gh2 plus p2. Now we can write in this way 1 by 2 q1 square plus gh1 p1 upon rho 1 rho is equals to 1 by 2 q2 square plus gh2 plus p2 upon rho 2. Okay, so in this way we can see this is the Bernoulli's equation. It represents the conservation of energy. So this is all about the conservation of energy and the application of the Bernoulli's equation. Now we have a theorem, that is Torricelli's theorem. This is also based on same concept that we have Torricelli's theorem. Torricelli's theorem says that if you have a tank which is closed, it is closed basically. We have a tank and it is closed. I say it is not, like there is no atmospheric pressure and same atmospheric pressure. Then the pressure in this way, this is the fluid and fluid passing through this output. So the area is basically A2 and this is the A1. Velocity is Q1 and velocity is Q2. The height from we have taken the reference line here only, or it is the like bottom. So we will take this as h. Okay, this as h1 and basically this is your h2, that is 0. Okay, h1 h2, that is basically the 0. Here it is h2 is equals to 0 with the reference line, negligible. So we will consider it as 0 with the reference line. Let the pressure on the surface at the inside are P1 and P2, then work done is basically F2 del 2 x2 minus F1 del x1. Then it is basically P2 area. We can write in this way P2A2 del x2 minus P1 A1 del x1. So we can write it is basically P2 V2 minus P1 V1, but the volume are same. So we can write P2 minus P1 into V1. Now in the previous section we have written as the P1 minus P2, though it is like different thing, that it vector like work is basically the vector quantity in this way, like if F is a vector quantity and dr like r is the vector quantity and the displacement is a vector quantity, then it represents the like direction of the like works. Okay, like the no effect of the P2 minus P1 or P1 minus P2. Now here h1 is the height of surface of water. Okay, height of surface of water. So basically it is till here. Okay, it is the surface of water. Then and h2 is negligible, that is the outlet height. So work is basically kinetic energy and static energy, that is basically work is equals to the kinetic energy plus delta U. So it is 1 by 2 m q2 square minus 1 by 2 m q1 square, the difference, and it is mgh2 minus or mg, okay, we will take it as 1 minus 2, okay, then it is mgh1 minus mgh2. Here h2 is 0, so basically it will be 1 by 2 m q2 square, and it is basically p2 minus p1 into v minus 1 by 2 m q1 square plus mgh, where h1 is basically h, okay. Then it represents the Bernoulli's equation is 1 by 2 q1 vector square or simply q1 square plus gh2 plus p1 upon rho is equals to 1 by 2 q2 square p2 upon rho. How? The same process, but here h2 is equals to 0. In the same process h2 is equals to 0. Now by the condition like this what we have written, that m upon v is nothing but the density, that first we will divide v both the side and then we'll separate all the terms in this way. Here h2 is nothing but your h, okay. Now next, basically we want to find the velocity, at the output or at the outlet. So what will be the velocity by the condition, or basically continuity theorem, that is q1a1 is equals to q2a2, velocity into area is equals to velocity into area. So it will be q1 is basically q2 into a1 upon a2. So we'll put this, so q2 into a1 upon, we'll put the value of this, then the value of q1, then a2 upon a1, so a2 upon a1 all square plus gh. We'll put this value in this equation, plus p1 upon rho is equals to 1 by 2 q2 square plus p2 upon rho. Now we have 1 by 2, this will be q2 square a2 upon a1 all square plus gh plus p1 upon rho is equals to 1 by 2 q2, okay. It will be q2 here. Then q2 square plus p2 upon rho, just simplify it, it is 1 by 2 q2 square, will take it here, then we can take common, so it will be a2 upon a1 square all square minus 1 is equals to p2 upon rho minus p1 upon rho minus gh, okay. Basically h2 is h now. So we'll find the q2 square, it is 2 upon a2 upon a1 all square minus 1 minus, or basically into p2 upon rho p1 upon rho minus gh. So the value of q2 is nothing but the under root of 2 into p2 upon rho, or basically we can write p2 minus p1 upon rho minus gh divided by a2 upon a1 whole square minus 1. Then we can write if p2 minus p1, yeah. Next, if tank is the special case, tank is open, then p1 is equals to p2. If tank is open, then it will be q2 at root of 2 gh divided by divided by, if there is minus, then we can write 1 minus A2 upon A1 whole square. Here A2 is very less than A1, then A2 square is very less than A1 square. It means A2 by A1 whole square tending to 0. So Q2 is nothing but root 2gh. So this is basically the free falling object, the velocity of free falling object or the free falling fluid. So this is all about the Torricelli's theorem and a particular case of the Bernoulli's theorem. So now in the next videos we will discuss some more example of the Bernoulli's equation like pitot tube and Venturi meter basically. So thanks for watching my video. Keep watching MS Maths. In this video we have discussed all these things. So thanks for watching my video. Keep watching MS Maths. If you like the video, then please subscribe the channel, share with your friends, and for more updates follow the YouTube channel MS Maths. Thank you. Bye bye.